Start with this last day of this beautiful conference. It is a pleasure for me to introduce Begoña Barrios Barrera from Universidad de La Laguna, Tenerife, España. And she's going to talk about the equivalence of weak and viscosity solutions in fractional non-homogeneous problems.
Okay. So thank you. First of all, I want to thanks to Joao and to Leandro again for this really good idea to organize this virtual meeting. So today I want to show you some results related with a non-local problem posed in a bounded domain and that involve a non-local and non-linear operator. And the statement of the result are quite simple. So, I mean, we are interested in proof the equivalence of two types of solutions, but the proof are really tricky, more involved. So all the results I want to show you have been obtained in collaboration with my friend, my colleague Maria Medina, and she spoke on Wednesday. And since we are living in this strange period, we are a bit nostalgic, I decided to post this picture. We were in a conference some years ago in the south of Italy, drinking a really good Italian coffee and enjoying this amazing view of the sea. So I hope we can meet soon again. So after this emotional moment, let's go to the math. Okay, so what will be our motivation? We'll show you in a second, and then I will move to the non-local framework. So the motivation of study the work comes from the classical P-Laplace operator, the P-Laplace operator that have been introduced on Wednesday, I think so, by Hernan. So we know that is this type of divergent operator, that is the generative P is greater than 2, a singular P is smaller than 2. So we could ask to ourselves if we put that the operator is equal to a datum in a bounded domain in the Euclidean space, if the different kind of solution of this equation are equivalent. And the first result that we can find in the literature is this paper, a very celebrated paper of Juutinen, Lindquist, and Manfredi. They prove it when the datum is equal to 0, I mean we are working in the homogeneous case, that the concept of viscosity super solutions is equivalent to the P superharmonic functions. Okay, the P superharmonic function are the generalization of Widries made for the superharmonic function. I mean, we understand that a function is in the class of the superharmonic, P superharmonic, if satisfies that is lower semi-continuous and also has a good behavior when you compare with a P-harmonic solution. So for instance, the fundamental solution of the P-Laplacian belongs to this class of functions. So in the literature, this kind of P-harmonic function have been treated like weak super solution of the problem. Because Lindquist in the 86 proved that more or less the both class of function are similar. I mean, if you are working with a P superharmonic functions, you could think that you are working with weak super solutions. So this theorem could be understood like the weak super solution is equivalent to the viscosity super solutions. So I think that all of us, we are used to work with this kind of concept, but weak is because we are working in the energy formulation of the problem. And viscosity, we have to think that we will attach our function from below for a suitable test functions, okay? So I repeat again that this theorem was done for the case f equal to 0. The proof that viscosity implies weak it was really involved and very rigid. So 10 years later, Julin-Juutinen proved an equivalent way of proving this implication. I mean that viscosity implies weak. And they also generalize the proof in the case when you have a datum that could depend of x and is continuous. So some years later, Medina and Ochoa generalized the result of Julin-Juutinen when you admit that your datums also depend of the gradient of u. You have here a function that has lower order terms that depend on the function u and also the gradient, okay? So let me go for a bribe to the proof of the Julin-Juutinen. Okay, they using the infimal convolution. So the infimal convolution comes in the convex theory, but they are really useful in the viscosity theory because they have really good approximation properties, and they are near to a C2 functions that are the suitable test function when we want to touch our solution and evaluate the operator. So the infimal convolution, what you are going to do is to take your function and then add this monomial here and take the infimal of the inner region, okay? So here in this picture, the infimal convolution is the orange or the yellow one, and the supremum convolution that I'm not going to define it is like when you take the supremum here and a minus here will be the blue one, okay? So if you are working in the general case, if P is greater than 2, then Q will be equal to 2. And in the singular case, you need to put an exponent that is bigger than 2, okay? So as I told you, these functions, U epsilon, will have good properties in order to recover the information that you have in your equation of U. So, okay, let me try to summarize the good properties that we have. If I give you a function that is bounded, lower semi-continuous, then the first property is that your infimum could define not in omega, in the intersection of omega with a ball with a radio r epsilon that goes to 0 when epsilon goes to 0. Moreover, you will have that this sequence of function is an increased sequence that converges almost everywhere to a function u, also is locally Lipschitz, and also, since it's semi-concave, is twice differentiable. And also you have the control of the Hessian in the domain WR epsilon. The domain WR epsilon is good that you bear in your mind during all the talk. We are working with points that are in your domain, but the distance between the domain and the boundary has to be bigger than this R epsilon. But remember that will goes to 0 when epsilon goes to 0. Okay, so more good properties of these infimal convolutions. When you are working with critical points, then you are assured that your function is equal to your infimal convolutions. And moreover, you have that the Hessian is definite semi-negative. Okay? So the last property is the following one that we will use in our singular case. When you have a point in your domain WR epsilon, always there exists another point such that your infimal convolution will be equal to the function that is inside the infimal. So think about that this function is a function of x. So if we remember, in terms of x, this function phi will be smooth. So this is a good thing that we have to keep in mind too. So we have to evaluate our function, the infimal convolution, equal to a suitable function, okay? So with this infimal convolution, Julin-Juutinen proved the result. Then Medina and Ochoa adapted the proof in order to work with the gradient terms. So what is our objective now? Okay, I want to work with a non-local operator that is the fractional P Laplacian operator. So here we will have two main protagonists. First of all, we have the fractional P Laplacian that I think that Hernan also introduced us on Wednesday. So let me speak about this operator for a moment. So there is a non-local operator because in order to evaluate the operator, you need the information of the function u in all the space. It's defined in a principal value sense, so this will be really important for us. And of course, when P is equal to 2, we have the classical fractional Laplacian operator that Ireneo spoke a lot about this operator yesterday. And when S goes to 1, you can recover the classical P Laplacian operator. So along the talk, sometimes I will write L of ux minus uy in order to instead of write this expression, okay? This function will be really important for us because it has good properties. So before moving to explain you where is this other guy, other protagonist, I think that we have to stop here for a while in order to think which kind of function you can use if you want to evaluate this operator pointwise. I mean, you have your principal value. So since you have your principal value and this term is odd, you can add the L evaluated in the gradient of the function u. So you could have the cancellation, and in the numerator you have the modulus of x minus y to the power 2. But this is the best you can get. I mean, if your function is C infinitive, so you cannot get more than the power 2. So you have a problem. If p is smaller or equal than 2 over 2 minus s, your operator is not well defined even if your function is C infinitive. Because I repeat again, you cannot get a power bigger than 2 in the numerator to cancel the singularity of the operator. Okay, this is something important that we have to remember. Okay, so let's go to our other protagonist, that is this kind of fractional derivative. So in order to explain you correctly what is this guy, let me go for a second to the linear case. I mean, let's go to the case when p is equal to 2. So when p is equal to 2, we have this bilinear form that appear when we work with the energy formulation of the problem. So it's the non-local counterpart of the product of the gradient of u times gradient of b. And when you substitute the v by u, then you get the term that appear in the energy functional when we are working with problems that involve the Laplacian, okay? So we can generalize this idea. So for every p, what we get is this term that of course is not bilinear because it's not linear in the first component, but we keep the notation in order to remember to you that comes from this idea. So this could be written as the non-local counterpart of this product. So when you put v equal to u, what you get is the same idea of the modulus of gradient of u over p. And this operator dps is homogeneous of degree p. So the condition, the growth condition that you are going to require to your datum will be the same as Medina and Ochoa put in the paper. We will see in a second, okay? This operator DPS appears in other works, for instance, a recent work of Caffarelli and Davila, other work of Davila, Sire, and Abdelawi, Fernandez. I'm missing names for sure right now, okay? So before moving to our definition of the solution of our problem, let me mention to you that there are many works with this fractional p Laplacian appear. Don't scare now. A lot of names, a lot of properties, regularity, existence of lemma in some particular cases. But I want to highlight this particular work that Korbenpa, Kusi, and Lindgren proved 2 years ago, or last year, that if you put in the right-hand side the homogeneous datum, I mean, if you put f equal to 0, then the equivalence of the viscosity and which solution is true. I mean, Korbenpa, Kusi, and Lindgren proved the same result as Manfredi and his collaborator proved in the celebrated paper. Okay, so what happens if we remove the hypothesis f equal to 0? I mean, what happens if I put a general datum? So as far as we know, the only result that we had was obtained by Servadei and Baldinocci for the linear case, and only when f depends of x. So the problem is completely open, and we think that is will be interesting to understand what happened with this general case. So this is our objective. Our objective is to establish the equivalence of the notion of the solution to our problem when we have this fractional derivative here and a general f that satisfies some property that we will see in a while. So now I have to define you what is the weak solution and viscosity solutions. So the weak solution is the usual that we are used to work with. We have the fractional Sobolev space with the Gagliardo semi-norm, and we have to require some decayment of the solution in order to have the operator well evaluate when we test with a function. So this is the notion of the weak supper solution. If we have a good test function that is positive, if we have a function that is in the Sobolev space and have the good decay property, then this inequality is true. So remember that here you have another integral, okay? So for the people that is used to work with a non-local problem, here you will have the double integral in all the space Rn times Rn. But since your function has compact support, let's say K, we are used to write here this double integral in the space Qk, that is K times Rn plus K, the complementary of K times K, okay? Of course, the notion of subsolution is if you have a supper solution minus U will be the subsolution, and the concept of solution is if you are supper and sub at the same time. Nothing new. Okay, so let's go to the viscosity sense. In the viscosity sense, we have to stop a bit because you have to remember that I told you that when P is smaller than 2 over 2 minus S, you have problem when you want to evaluate your operator. So if you want to touch your function from below for a suitable test of function, you have to be clear in your mind what is suitable in this case. So since what you want to do is when you have a critical point, you want to touch with a monomial like x to the power beta for some beta bigger than 2. But you need some flexibility in order to choose your test functions. So this is the reason why Korbenka, Kusi, and Lindgren introduced this space. So don't be scared about that. You have to think that you are comparing your gradient with the distance to the set of critical points, and also the same with your Hessian. So you keep in mind that which kind of function are in this particular set? Well, the monomial that is good plus some suitable perturbations, okay? So the good thing is that in the critical case, I mean when P is smaller or equal than 2 over 2 minus S, your operator is well defined and also is continuous when your function U belong to this space, and always you will require the good decayment, okay? So remember that when you are working with P greater than 2 over 2 minus S, C2 is enough. If we are working in the singular one, we have to require to belong to this particular space. But always when you are working with critical points, if you are far away the set of critical points, C2 will be enough too, okay? So now you can choose your test function in the viscosity sense. So let's go to the definition of the viscosity solutions. So here, a lot of information, but remember, what you are doing is touching your function from below for a suitable test. What is suitable? Well, depends. If you are in the critical case, in the singular case, you have to require more regularity. And if you are in the not critical case, and also you have your gradient that is different to 0, then you only require the C2 regularity. Two things important here. The first one is that even if you are working with the datum equal to 0, since your problem is local, you always have to keep in mind the option that your test solution could have gradient equal to 0, because your constant solution are false solutions here, so you have to take care. And the second thing is this hypothesis that I put in a box. This hypothesis tells you that you will consider test functions that are beyond your solutions in all the space, your supper solution, sorry, in all the space. So normally, in many applications, you could write this definition in a more general case, only requiring the test solution to be beyond your function in a region of the point. And outside the region, outside the ball, you could put depth C equal to U. But in our case, we cannot do it by this guy. If we remove the dependent of this guy, we can put the notion of solution that we are used to. But again, I want to remember that this is a non-local operator, so you have to work more. Okay, so now we have the wick and the viscosity, and let's move to our first result. The first result says the following. If you have P between 1 and infinity, you have your equation, your non-local fractional derivative here. So if F has reasonable hypotheses, I mean, these hypotheses are the same as Medina and Ochoa put in their paper. So you have uniform continuous function that is not increasing in the second variable, and Lipschitz continue in the third one. And also you will need this growing hypothesis. So in this case, if you have that a viscosity solution is bounded, then supersolution, sorry, is a viscosity supersolution is bounded, then will be a weak supersolution. Okay? So how we can prove that? We will borrow the idea of Julin-Juutinen. We will work with the infimal convolutions. Why we will work with the infimal convolutions? Because I told you a lot of properties that this kind of function have. But in the local case, what is really important is that since you have this point-wise expression of the P Laplacian, you can transfer the information that you have of the Hessian of the U epsilon to the operator. Okay, so this is really useful. You have a point-wise expression with the Hessian of the function U here. And moreover, in the singular case, since you have to work outside the critical points because they are singular, they create problems, you can prove without a lot of effort that in the critical set, your function has the correct signs, okay? So these two facts helps you a lot in the local case. What happened in the non-local one, in the non-local case, in the non-local framework, first of all, our point-wise expression of the fractional P Laplacian involve this kind of fractions. So what you have to do is to transfer the information of the Hessian of the infimal convolution to this kind of term. And this is not simple at all. Moreover, you have two limits to consider. You have, if you want to pass to the limit, because you will work with your infimal convolutions, and then you will pass to the limit in order to recover your original problem. You have two integrals. One comes from the weak formulation, as in the local case, but you have another one that comes from the non-local operator. And moreover, we have another problem. We have a singular case. And in the singular case, we need to regularize the operator because, as I told you, even if your functions are C-infinitive, you cannot evaluate the operator point-wise, okay? So there are many complications that appear in the non-local case that need a lot of effort. So let me try to convince you, and not boring you, of the idea of the proof. So, as I told you, we borrow the idea of infimal convolutions. Our infimal convolution, you could imagine that we have to define for every function, for every point in all the space, because our problem is not local, but our U is defined in all the space, so we can take the infimal also in Rn. So, as in the local case, we can find an R epsilon that goes to 0 when epsilon goes to 0, such that this infimal could be written in this ball. And making a translation, this infimal could be written in terms of our function phi zeta. Remember that its function is the expression that we have in the interior of the infimal. Okay? So the first step in the proof is to have that if U is a viscosity supersolution, then the infimal convolution will be a viscosity supersolution too. But in the domain that I told you before, there are the set of the points whose distance is bigger, whose distance to the boundary of omega is bigger than R epsilon. and with the datum that changes a bit, okay? The datum will be f epsilon and will be the infimum of the f when we are working in ball center of the point x. So the proof of this result, I want to tell you that if you remove the third variable, the dependent of the fractional derivative, again, as I told you, you could put here the notion of viscosity solution that we are used to work with. I mean that you only require that the test function is below your solution only in the ball, okay? But here you have to take care with this guy. So, okay, this first step is more or less standard. You can do it with a bit of care, but also what you have, what is really important, is that you have that almost everywhere the fractional Laplacian of this u epsilon is bigger or equal pointwise of this f of epsilon. Okay, and I want to show you the proof of this fact, because it's quite different from the local case. So if we are working in the non-singular case, I mean I have a point in our domain and our p is greater than 2 over 2 minus s, and it's not a critical point, the proof is simple. Why? Because since your u epsilon is a semi-concave function, the Alexandrov theorem tells you that you can write your the Taylor expansion of u epsilon up to order 2. So this function, that is the Taylor expansion of u epsilon in the point minus a delta times the identity, it will be below to your u epsilon. And it's regular enough, it's C2. So you can take that this function in a ball that is containing your domain, and outside the ball, you can write the u epsilon that is below your function u epsilon, okay? So this is quite easy. So what happened in the critical case? In the critical case, you have to take care with you have to take into account that you are working with critical points. So in the local case, what Julin-Juutinen made, and also Medina and Ochoa, is to work with the set of points that has not a gradient equal to 0. And then they use the good property that I mentioned to you before. In this critical set, you have the control of the sign of your f. And this is not true here. So we have to use another different idea that is the following. It's quite simple after you realize that you have used it. So in the critical case, since your gradient is equal to 0, then the good property of the infimal convolutions tell you that, in fact, your function is equal to the infimal convolutions. So, since the infimal convolution is an infimum, what you get is that this function, uy, the uy will be bigger or equal u in the point x0 minus this monomial. And this is a good test function. We can use this guy. We can use this guy taking this function in a ball and u epsilon outside the ball. So we will take this as a test function in the viscosity notion of solution of u, not u epsilon. This is important because think that if you put here a u, you will not recover the problem in a point-wise way of the u epsilon, because thinking that what you want to write is the problem in terms of u epsilon, okay? So you take this test function and you use a very important fact, that is the following. When you have a street table function, then the principal value in a small ball goes to 0 when the radius goes to 0, okay? So what is more or less the same, the fractional Laplacian of a street table function can be controlled by the operator outside a ball and a small term. So this allows you to recover the problem satisfied by u epsilon, okay? But this is really important. You have to work a lot to prove that. Okay, so the first step, we know that your u epsilon satisfies this inequality in a pointwise way. Okay, Second step, really tricky point, okay? This is what we have proved, that we can pass from the point-wise definition of the operator. Now, if you want to get that your U epsilon is weak, because remember, we are coming from viscosity solution and we want to arrive to weak solution. The way to prove it is, first of all, prove that your U epsilon is a weak supersolution and then pass to the limit. So the second step is to prove that your U epsilon is a weak supersolution. So if you want to prove that, you need this inequality. Remember, here you have another integral that comes from the non-local operator. And to prove the second step, you have to work a lot. Why? Because we have many problems. So you have to regularize your infimal convolution because they are not good enough in order to make the integration by parts, okay? Of course, you can use the good property that have your nonlinear terms, but in the singular case, you need to regularize not only the U epsilon, also the operator, because remember, I tell you again, the operator is not well defined when P is smaller than 2 over 2 minus S, okay? So you need to regularize your operator and use the good property that I mentioned before, that if you have a point in your domain, always there will exist another point such that your infimal convolution will be equal to this function that was the function that was inside the infimal, and it's good. So since you can control your non-local operator in the small ball when you have the singularity, in terms of the non-local operator of the function C, to apply the factor lemma, this is enough, because here you have the control of this integral because your function is regular, okay? But you have to work a lot to pass to the limit twice, and this is a mess, okay? But forget about that. What we have here is that our U epsilon is a weak supersolutions. The last step is the following point. Under the suitable hypothesis of our function f, what you have is that if this limit is equal to 0, and this could be obtained using the shape of the operator, then you will have the convergence of the datum. I mean, if you want to pass to the weak formulation of the function U epsilon, you have to pass to the limiting two terms. In the left-hand side, you have the weak formulation of the problem here, and in the right-hand side, you have the integral in terms of f epsilon. So this third step allows you to pass to the limit in the right-hand side, but only if you are able to guarantee that this limit is equal to 0. So now you have all the tools to prove the result. So summarizing, by step 1 and 2, you have that U epsilon is weak supersolutions. Now you want to prove that your U is weak supersolution. So you can take a test function with a compact support. Since R epsilon goes to 0 when epsilon goes to 0, you could take a small epsilon such that your compact is contained in your domain. Now you can obtain a Cacciopoli type estimate in order to have that the Gagliardo semi-norm of the function U epsilon is uniformly bounded. So this allows you to pass to the limit in the right-hand side. I mean, this allows you to pass to the limit when you have the double integral, because you have the suitable convergence using the compact embedding of the Sobolev spaces. Working a lot with this force, it's a tedious computation. Choosing a particular test function in the weak formulation of the U epsilon, what you get is that the hypothesis of the third step that I showed you before is satisfied. So now you can pass to the limit and recover the weak formulation of your problem U, okay? So in the last minutes, let me speak about the reverse theorem. I mean, we have proved that viscosity implies weak. and these have made with a lot of efforts. So now let's try to do the reverse. What happens if we think about the weak implies viscosity? Okay, so this result is strongly connected with the fact if you have a comparison principle theorem or not. So in this point, I want to encourage everyone to prove comparison principle for the P fractional Laplacian operator when you have a general datum. I mean, if you go to the literature, you could find many works related with the linear case. If you have the good control of the operator of two functions, you have the minus the fractional Laplacian of u bigger or equal than the fractional Laplacian, the P fractional Laplacian of v, and the function are well ordered outside the domain, then without many effort, you could prove that the solution, the function are well ordered inside the domain. But if you put a datum that depends of you, there are not much known about that. I mean, there is a paper of Del Peso and Quas with a particular datum in the right-hand side. So in this case, under some suitable condition of the function, the hypothesis that they put, we could prove in this particular case that the viscosity and the solution are equivalent. But what we have is that there are not any reasonable general comparison principle for this kind of equation. So suppose that we have a comparison principle. If we have a comparison principle and a continuous weak supper solution, then if our datum is Lipschitz continue in the third variable, of course we keep the continuity of the datum with respect to the third variable. The weak supper solution will be viscosity supper solutions. And the proof of this result is more simple than the previous one. This is the reason why I decided to show you the previous one, because has it's more involved and you have to take care of the definition of the operator, work with the infimal convolution. But this proof is not easy at all, because you have to work also and take in consideration that your fractional P Laplacian operator and also your fractional operator ds satisfies this kind of property. I mean, the operators are continuous under some small enough and regular perturbation of your function f. And you have to use that because the non-local nature of the problems obliges you to change a bit the strategy that the author made in the local case, because your solution doesn't match very well with the constant. I mean, you cannot perturbate with constant function. You have to take care and make the perturbation in a different way. But if you work with this switchable property, that could be also applied in the case when you put here your fractional P Laplacian operator, then you could prove the second result, that is weak implies viscosity. So I don't know if I have time or not. I think that I have spoke very fast because I began 5 minutes later. I have more time, Hernan, or not?
Well, we started a little later, so you have like 2 minutes left.
Okay, so it's 2 minutes. I don't want to bore into you more. Okay, so I stop here.
No,
okay, no, I think it's okay, because I want to show you a bit the proof of weak implied viscosity, but I think that, okay, don't worry about that. I think that I can stop here. It's more reasonable. So let me thank you for your attention. It's really weird to speak without see you, but thank you. And I want to quote this sentence that Nuremberg said, that said, if you go to some part of the world, you will always find a friend that could understand you, because we speak the same language, that is math. So here we are doing the same, but in our case, it's really strange for me. So I hope this situation change fast. So thank you again. Okay, thank you so much, Begoña, for this beautiful talk and this beautiful quote from Nuremberg. And let me tell everyone that you can make a little applause reaction in the Zoom. So
even if we cannot applaud like personally, we can make applause reactions. So do we have any questions for Begonia from the audience?
I have a question. Could you consider or prove similar results for operators with non-standard growth, like px Laplacian or operators with Orlitz-Sobolev structure?
Okay, yeah. I don't know, because I suppose you have to require some hypothesis in the px exponent. I'm not an expert at all of this kind of operator. I don't know. We have to think about that. Of course you can, I didn't mention to you, but of course you can change your fractional p derivative for other ones. This is something that you could also ask to yourself. But to change the operator and put something that depend of the x, I don't know. You have to work much more, because you need some uniform estimate, Cacciopoli estimate, so could be, I don't know.
Okay, thank you, Begonia.
Thank you. So I have another question. Do you think it would be possible to sort of like take a limit as p goes to infinity and get a result of the same flavor as you have, but for the infinity Laplacian, for fractional infinity Laplacian or something like that?
You know, the problem is that your estimate depends on the p. I mean, so I don't know if you have the uniform and convergent there, no?
Okay.
I don't know.
Mm-hmm.
I mean, in the previous lemma that I showed you, I didn't tell you, but the estimate that you have to do in order to prove this result depend of the p. So you have to take care if you want to pass to the limit there.
So it could blow up as p.
Yeah, I don't know. Mm-hmm. Could be. If you are interested with that, I recommend you the work of Squasina and Bucure-Squasina. They published recently about the version of the infinity non-local operator.
Okay, I will look it up. Thank you. Okay, do we have any other questions?
I have a question. I have a question, Edwin from Chile.
Hola, Chile. Hola, Edwin.
Do you know, you said that the comparison is not known in general, but for instance, in the linear case for p equal 2, but with this capital D2 operator, the linear, it is known? It is known, this comparison principle?
I don't know it. You know, we tried to find a reference and we didn't find much more about that. I mean, if you are trying to prove the same result as Serrin and Pucci prove in the local case, that is the most general that we know, we didn't find anything in the non-local case. So the first step, of course, is what you said. Try to prove it in the linear case, and then try to adapt it in the non-local, in the non-linear one.
You mean the proof in Gilbert and Trudingen?
Yeah.
Yeah. So this is not known.
We don't know it. Yeah, we didn't find the reference. In fact, since this work, okay, this is a recent work. What I mean recent is that it will be in archive on Monday maybe, but we encourage, if someone of you, this was one of the reasons I want to give you this talk, because if someone of you knows, of course, a comparison principle, even in the linear case, please tell us, because we didn't find any good reference to put it. We are really limited. If we add a non-local fractional derivative in the datum, we don't know anything.
Okay. I talked with
you have homework.
I was waiting for your result.
Okay, thank you. I'm glad that you're interested.
Okay, thank you.
I think that Ireneo is writing in the chat.
There is a comment by Ireneo in the chat that says that perhaps you have a comparison principle properties, some p sublinear behavior in U is needed.
Yeah, I think that general comparison principle property in general, with this kind of generality for the second member, is quite difficult to believe. But there are several things. For instance, if you has not the the part of the gradient, the fractional gradient. Then there are perhaps some kind of result like the Susanna Camin and Bretis local, or where we are writing this in the linear case in for instance, could be useful. And in the second place, if you are independent, not dependent on you, and dependent in gradient u, where is the local gradient I saw yesterday that there are a comparison principle you are under the critical level.
Yeah, but the problem.
But it is interesting to find what is the critical level where you are the P Laplacian.
Yeah,
this is a good point to think.
Yeah, but the problem here is that if you put the local gradient in the right-hand side,
right,
the things change a lot. I mean, I think that this is another point of view, because, for instance, the catch-up, you cannot recover the information from the datum to the operator, so the catch-up poly, I don't think will be true. And also, okay, I think that the problem will change a lot, but I'm agree with you that if you put the gradient and you lose the non-locality property in the right-hand side, they are maximum principle and comparison principle.
But only in some with some type of growth in the
only with some type of growth,
Because if no, is not true.
Yeah.
Really not true. In the critical case, we have the case of the Laplacian in the local case with gradient square, and we have a lot of infinitely many solutions for the problem.
And also you have to take care with the S, because if we want to write a gradient, you have to require that S bigger than 1/2 or whatever.
But must be something similar in this case.
Yeah. Continue working.
Yes, of course.
Thank you.
Okay.
Okay, so thank you for all the questions, and let's thank Begonia again for this great talk. Thank you so much.
Thank you, all of you. Thank you.